You know, I have one simple request, and that is to have sharks with frickin' laser beams attached to their heads. Now, evidently, my cycloptic colleague informs me that that can't be done. Can you remind me what I pay you people for? Honestly, throw me a bone here. What do we have?
Well, Dr. Evil, we were thinking about something pretty stupid with sea bass, but let's just put the hold on that and let's go take a look and see if we can figure out how to actually get your freaking sharks with lasers. So what are lasers? Well, lasers are light amplification by stimulated emission of radiation, which is a tongue twister, but ultimately lasers are photons of energy. They are coming from a source, and there's all sorts of different types of lasers, but today we're going to be going over 5 different types of lasers and what they can do, and if they can actually be mounted on a freaking shark to be able to pull this off for Dr. Evil. Our first laser type, CO2 lasers, are typically used in the hobbyist market, but at higher power levels can be used in metal fabrication. Number 2 is diode lasers. Diode lasers are used in many different everyday applications, from barcode scanners to CDs and DVDs. All sorts of different applications use diode lasers. Our fiber lasers are our third type of laser, and they are used in many different applications as well, specifically in fabrication, and they could be promising. Our fourth type is Excimer lasers, which tend to be used in micro applications, and our fifth type are solid state lasers. And solid state lasers are very interesting, and we'll get that towards the end of the video. But first, let's figure out what lasers really are with a video by the engineer guy.
In 1960, Ted Mayman demonstrated the first laser by taking a cylinder of ruby and surrounding with a xenon arc flash lamp used in aerial photography. An intense burst of light from the lamp initiates lasing. To see how it works, let's look at what happens with a weaker lamp. A flash would promote a few electrons from the ground state to an excited state. They'd lose a bit of energy, fall to a lower energy state without emitting light, and then drop from there to the ground state, giving off a burst of light. The light produced would be incoherent light, a spectrum of colors and intensities, just as my small laser made the ruby sphere glow. To create a laser takes an extremely powerful lamp. In the ruby laser, repeated flashes, called pumping, make something amazing happen. They supply so much energy that a population inversion occurs. Here, more electrons in the energy level just above the ground state than in the ground state. Electrons from a population inversion returning to the ground state release light that starts an avalanche called stimulated emission. The photon produced when an electron decays induces other excited electrons to simultaneously decay and release nearly identical photons. That creates coherent light, meaning that the crests and troughs of every light wave in the beam match up. Now, at this point, we have coherent light, but not yet the other two properties of laser light. To get a narrow beam with all the light rays parallel and of a nearly single wavelength requires an addition to the ruby rod. Mayman silvered the ends to reflect the light within the ruby cylinder. He made the two ends of the rod astonishingly parallel to each other. From top to bottom, the distance between these two mirrors differs by no more than 200 nanometers. Inside this resonant cavity, two things happen. First, any light rays that don't line up with the axis eventually just exit out the side of the cylinder, and the light parallel to the axis becomes intensified and narrowed in wavelength. The mirrored ends create a standing wave, which means only light of particular wavelengths can exist inside the cavity. By choosing the rod length correctly, we can get the nearly single wavelength of light characteristic of a laser. A small hole in one of the mirrors, or a partially silvered mirror, allows the light to escape, creating the familiar beam.
Now that we've gotten that overview of lasers from the engineer guy, let's think about what type of specific laser will be used for our freaking sharks. So with that said, let's take a look at CO2 lasers and see if they might be the ticket for the sharks.
It's a glass tube with gas sealed within, namely carbon dioxide and some nitrogen. High voltage electricity is passed through the tube, which excites the gas particles and produces an invisible beam of high power infrared light, also known as a laser beam. Now if we have a look at my current laser machine, we can see the laser tube here in the back. The laser exits the end of the tube and is immediately bounced on the first mirror, down to the second, over to the third, down the head and through a focusing lens that's inside the nozzle and onto the workpiece.
CO2 lasers are awesome in the hobbyist market and can be used at your house to be able to cut wood, fabric, leather, and even metals at higher powers.
So in this video we will see how a laser diode works. In previous episodes, we saw how a common diode as well as the light-emitting diodes worked, so this time I will not go into much detail regarding the passage of electrons through the different materials, but we do have to understand in broad terms the process by which light is emitted. In a light-emitting diode, we will generally have two semiconductor materials joined together, on the one hand an N-type semiconductor that has an excess of electrons, and whose charge carriers are the electrons themselves. And on the other hand a P-type semiconductor that has a lack of electrons and whose charge carriers are the gaps left by the electrons. When these two materials are joined and connected to a battery in direct polarization, the electrons will pass from the N-type semiconductor to the P-type semiconductor. When this happens, what is known as spontaneous emission will occur. At the point of contact between the two materials, electrons and gaps will recombine, and due to a difference in the amount of energy that electrons can have in the atoms of each semiconductor, a photon will be released. While this recombination occurs spontaneously whenever an electron and a gap are in close proximity, this can take a short period of time, on the order of nanoseconds. During this time, what is known as stimulated emission, which is part of the acronym LASER, can occur. More specifically, if a photon with the needed energy passes through the place where an electron and a gap meet, it will cause them to recombine, and the new photon will have the same frequency, polarization and phase as the first photon. To enhance this behavior, laser diodes also have an intermediate semiconductor layer, which has a dual function. Firstly, to promote the recombination of electrons and gap in a given volume, and secondly, to function as a channel for the photons, because, given that it has a different reflection index to the other semiconductors, at certain angles, the walls will behave like mirrors. At this point, although we will have a certain amount of photons generated by stimulated emission, we will continue to have mostly photons generated by spontaneous emission. To achieve this goal we will need an extra element, reflectors. At one end of the semiconductor array we will put a fully reflective coating, and at the opposite end we will put a coating that is highly reflective, but lets out a small amount of light. This arrangement generates what is known as a Fabry-Perot resonator, in which the photons continuously bounce back and forth between the two ends, continually generating more stimulated emission and allowing the light beam to exit from only one end. However, we still have another problem. Even if the oscillation frequency and phase of the photons is exactly the same at the time of emission, the phase can vary each time the photon is reflected. To exemplify this, let's analyze the photon only as a wave and trace its trajectory. If we compare the trajectories generated each time the photon moves in the same direction, for example, from left to right, we will realize that the phase is changing and as a consequence the photons that will go outwards will not be temporally coherent. Fortunately, the solution is quite simple. We must adjust the distance between both ends to be a multiple of half the wavelength of the photons we want to amplify. Let's suppose for example that this distance is equal to 3 times half the wavelength. This time, if we trace the trajectory of a photon, we will realize that every time it is reflected it follows exactly the same path, no matter how many times it happens. In other words, we will be creating a standing wave, and the photon beam that will eventually go out will be coherent in both frequency and phase. We would only be missing the last detail. Although the photon beam will be temporally coherent, due to the randomness in the direction in which the photons are emitted at the moment of recombination, the resulting beam will have a small spatial dispersion. Because of this, a lens is usually integrated. This lens redirects the photons and makes them all travel in parallel, or in more technical terms, generates a collimated beam.
Diode lasers are used in everyday applications because they're so cost efficient, but at the same time, their current constraints and power constraints are really going to limit us on the shark. So we've got to move on from the diode, so let's take a look at fiber lasers.
Its Greek symbol lambda. In the optical spectrum, wavelength refers to the color of light. Blue is a shorter wavelength, around 400 nanometers, and red is a longer wavelength, around 700 nanometers. Light, of course, extends through a far greater spectrum than the human eye can see, from X-rays through to terahertz radiation. Most optical systems operate from the UV through to the infrared. Optical fibers became possible with the practical understanding of Snell's law. Light transitioning between transparent materials bends in proportion to the change in its velocity. Like a rod in a beaker appears bent at the air-water interface. The ratio of the velocity difference is the refractive index. In optics, we add materials called dopants into glass to change the refractive index. By putting two pieces of glass with different refractive indices adjacent to each other, we can emulate the bent rod effect. Imagine that a glass rod with a high refractive index core surrounded by a low refractive index cladding would guide light continuously down its axis. Well, that's exactly what happens. And we can also change the effective angle at which light is accepted by adjusting the refractive index of the two glasses. This is called the numerical aperture. High numerical aperture means broad angles of acceptance. If the core size is large so that multiple wavelengths of light or modes can enter by a variety of angles and can propagate down the core is considered to be multimoded. If the core size is small enough to only allow the passage of one wavelength at a specific injection angle, the core region is considered to be single mode. Depending on the size of the glass rod, the refractive index, and the wavelength, the core can be both single or multimoded.
Fiber lasers operate at a lower wavelength than what CO2 lasers do, so they may be a good use for this application because of the power that can be absorbed by the object from the fiber laser. So let's hold on to that one, but let's also move on to the Excimer laser.
The WaveLight EX500 Excimer laser features a completely sealed, nitrogen-flushed beam path that is checked in 3 separate locations for energy and consistency, thus setting the standard for both laser precision and durability. Pupil dilation causes pupil centroid shift, or a shift in the visual axis. The WaveLight EX500 Excimer laser is able to compensate centroid shift and make necessary adjustments to align with the predetermined treatment profile. The WaveLight EX500 Excimer laser maintains a high pulse frequency with a minimized thermal load, allowing only 1 in 5 pulses to overlap.
Excimer lasers tend to be used in micro applications such as eye surgeries and are truly groundbreaking in what they've allowed us to do in surgical purposes. But we're not trying to do surgery with these sharks, we're trying to blow stuff up. So let's move on to the solid state laser. And specifically, when we're going to move on to the solid state laser, we're going to talk about the LAWS weapon system by the U.S. Navy. Boom! That's what I'm talking about. That's what we need for the laser shark, the LAWS weapon system. So now let's figure out how do we power this thing and what type of shark do we need to mount it on. Let's start out with the power. So we'll look at Ohm's law, which is voltage equals current times resistance, and also the power equation, which is power equals voltage times current. So with those two equations, we can figure out roughly, based on a Wikipedia article, that the LAWS weapon system uses about 15 kW to 50 kilowatts, which is what kW stands for, of power. So with that, we need to figure out our voltage and our current. The LAWS power is about 15 kilowatts to 50 kilowatts. And so at 24 volts DC, we now need to figure out what the current would be, which would be about 2,000 amps of current at 24 volts. That's a lot of current. Your average household breaker is 20 amps. So let's think about this. If we crank up the voltage, then we can decrease the current. So if we were to generate 240 volts, then we would drop our current by a factor of 10 as well. So we would drop to 200 amps, which is more reasonable in this application. So we could get a 50 kW generator to be able to help power this application. Now this is all theory, of course, and to be honest, there's a lot of practicalities involved, but we are talking about sharks with freaking lasers. So you got to be a little bit creative. So now that we know what size generator we need, now we can figure out what type of shark do we need. So we're going to look at three different types of sharks. A great white shark and a great hammerhead shark, which are cousins, and they're about the same size at about 6 meters long or close to 20 feet. Now that's a big shark, and I'd hate to run into it in the wild, but that's not going to be quite big enough to carry around the Law's weapon system in our generator. So let's move on to a whale shark. The largest known whale shark came in at 18.8 meters or 61.7 feet long. That's about the size of a school bus. Considering our generator will be about 1 ton, and we can assume the Law's weapon system will be somewhere in that vicinity as well, that means that the whale shark, as big as it is, might be able to pull this off, and if not, then we're going to have to go get a megalodon from extinction. So now that we've done our research, let's go back to Dr. Evil and show him his laser shark.
Open the tank. Open the tank!
Are those sharks with laser beams attached to their heads?
Thank you for watching this video. I really appreciate it, and I hope that you'll subscribe to the channel and join us as we try to make more educational content in a slightly entertaining way. So, thanks for watching. Have a great day.